Hello, everyone, and welcome once again to our Industrial Electronics and 4 session. I am C. Tobejane, and in today's session, we will be looking at rectification, which is Module 4 from the TVET First textbook by Macmillan and Troupant publishers. In today's session, what we will be paying our focus on is how to understand the process of rectification and filtering. So what we will do is we will start all this process from the transformer side, rectifying and then filtering, practically talking about a DC power supply. Now we've already learned from the book that for any electronic component that is present today, it needs to use a DC input. But because our electrical generation is from AC, transformers, they also contribute in tapping the electrical or signal that is there so that it is in AC form. So that AC needs to be corrected such that the output becomes a DC. I hope that our sketches that we're going to be doing today will simplify your understanding of this module so that then it becomes easier for you to attempt the calculations which are there. Now, what is a transformer? This is where we need to start. We know that a transformer is an electrical device used to step up or step down voltage. This means that the primary side of the transformer will be connected to the supply, which could be your power lines from the ESCOM or municipality. And your secondary side of your transformer will then be connected to your load. In this case, let us use a bulb. Now, the problem with an AC signal is that it does not have permanent terminals. This means that the terminals will change from time to time. How is that possible? This means that for a short period of time, this terminal will be positive with respect to this terminal. This means that our output signal will be in this fashion to the positive. So if this is an electrical component that only allows current to flow in the positive side and cannot withstand current flowing back into the negative side, let us assume that our component also has a positive and negative permanent electrode. This means that what we will see here is a glow in this light bulb. But because our transformer does not keep permanent terminals, it will then change its terminals once again such that this side becomes positive with that. So here, what we are expecting to happen is that we'll have the negative side of the sine wave, like that. But what will happen to this bulb? If it is programmed such a way that it does not or cannot handle voltage coming in from the negative side, it will then blow. This means that this bulb will no longer be able to function. How do we rectify that? First things first, we are going to apply what we call a diode or use a diode to rectify this problem of ours. This means that we will then be able to connect our diode in series with our load, positive and negative. Remember, a diode can only conduct current in the forward bias region, but it blocks the flow of current when now it flows in the reverse bias region. This means that when this terminal is connected positive with respect to the other terminal, the diode will allow current to flow through. Then our output will be as normal. But then when the transformer decides to change its terminals, having this side positive and the other side negative, this diode will then reverse bias. When that diode reverse bias, it clips off the negative side. Therefore, that means the light will switch off instead of burning out. The light will switch off instead of burning out, the diode will totally cut the flow of current in that particular instance. Until once again, after some time, the transformer decides once again to change back its terminals. That is, then now we are going to have another signal appearing there. So this means that the negative side of the sine wave is being clipped off. But this is not good. You cannot live in a household where when you're trying to turn on your TV, it will be on for a certain period of time and then off for another period of time, on for another period of time, and so forth. This is where rectification comes in still. So we've seen that this type of rectification could not achieve what we needed. We call this our half wave rectifier. Now, let us look at how our full wave rectifier will behave when connected to such conditions. However, the full wave rectifier is achieved by making use of a center tap transformer or by making use of a bridge rectification. Because the bridge rectifier and the center tap rectifier operate the same, they both have the same characteristics and the output is the same. In today's session, we're only going to be discussing about the center tap transformer. Perhaps in the future, we can then consider to discuss about the bridge rectifier. Now, what exactly is happening here? We have diode D1 and diode D2, whilst here we had only diode D1. This is called our full wave rectifier. When now, in this case, the transformer decides to make that terminal positive with respect to this one, this means that it will allow current to flow in this direction towards the load, come back again, and back there. In this case, we are going to have a glow. That means our output will appear like that. But see, at some time, we are going to see our current trying to take this direction here. But automatically, this diode will then block that current because then this will be in a reverse bias mode. But then it will again, when the transformer decides to change the terminal, making this side positive and the other side negative, changing this side to positive and the other side to be negative. This is what we are going to be seeing here. Let's try to fix that. This is what we'll be seeing here. The current will now be moving in this direction. Sorry. The current will now be taking this direction up towards the load, coming back, and then down. So at the very same instant, when the current tries to move in this direction, when it gets to that point, it will be blocked because then that will be in a reverse bias mode. Now, what is the output that we'll have here? Instead of having a total clip off, we will have another signal appearing there for D2. So this will continue on and on and on and on and on. So still what we are going to have is a light switching on and off, on and off, on and off. But the difference here is the time delay. We won't be having it off for a long period of time. But still we've not achieved what we needed to do. However, we have started to achieve rectification. So now we need to filter the circuit so that we see how the circuit will behave when it is filtered. The one most recommended filter that we can use is called the capacitor filter or a shunt filter or just a simple capacitor filter. We will begin off our filtering by filtering the half wave rectifier. That means we will connect our capacitor in parallel with our load, just like that. When we connect our capacitor in parallel with the load, just like that, it's such that when the current decides to flow in this direction, and then this positive appears here, we have conduction. And yet at the same time, our capacitor will be charging, storing energy, waiting for that moment to use it up. But when the transformer again decides to take current to this direction, instead of having a total clip off, what's going to happen is that the capacitor will slowly discharge to the load. Slowly discharge to the load, just like that. But we have a problem here. The discharge takes too long. So it means that our current will slowly be fading. If it's a light bulb, it will slowly be fading down to off and then on again, then slowly fading down to off. Somehow we are getting closer to what we need. What we are expecting to have here is a simple DC output. It will not be a perfect straight line, but something closer to that. This is what we are trying to achieve. Now, let us try to do the same thing here, right? We apply our capacitor in parallel in a full wave. What's going to happen there? Very simple. In this case, we will have a slow discharge like that. Can you see? So slowly we are approaching what we want. This means in this case, our new waveform will be like that. We will not have a complete switch off, but at least we'll be slowly reaching our DC. Remember, the DC output that we want should be that. That is what we are looking for. Now, what is the next step that we need to employ so that we see if we can be able to continue rectifying our circuitry? Is to introduce an inductor filter. We know that an inductor is a coil and it uses energy in the form of magnetic field. Right? Right. So let us go and see. We are going to use our inductor in a half-wave rectifier first. This means that we will still have our diode and our inductor, that way connected to our light bulb. Then, remember the output waveform before of this, when there was no inductor, it was like that and like that. See, the problem with an inductor is such that when it receives voltage, it absorbs that EMF in a form of magnetic field. And when the voltage reverses, it will then produce its own voltage. This means that if the voltage supplied to this direction is 5 volts, the inductor will also generate through magnetic field a voltage equal to 5 volts. But the problem is it then acts in an opposite direction, in a way thus creating its own waveform around that. So somehow then cancelling out what we already have. But considering that sometimes it will have some voltage spikes, that will be a bit higher than what we already had. So we need to fix this. How do we fix that? We can fix that perhaps by connecting our inductor to a simple capacitor filter. Let us see what happens. Now, this may be a half wave or a full wave, but I'll just take it from here. Having our diode, having our inductor, having our simple capacitor filter to the load. Now, what exactly happens here? The output waveform in this case, originally, when you are dealing with a full wave rectifier, this is what we had before. Now, what does the inductor do here? The inductor will create its own waveform, and yet the capacitor at the same time, it is trying by all means to filter everything out such that we have a smooth filtering there. If you can look at this, we are indirectly getting closer to what we need here. Slowly getting closer to what we need here. We want to achieve DC. We want to achieve DC. This is what we want to achieve. So we are getting closer. Now, what can completely achieve this? Let us see what happens when we put another capacitor before the inductor, changing this to an LC pi filter. When we change that to an LC pi filter, we may as well want to include a resistor in series with the inductor such that it will assist us in managing the voltage being produced by the inductor, RL. So when we have a scenario of that nature, we are now moving closer to achieving what we want. That means the output voltage that we have will be just there. So close to what we want because everything is just working up together. This capacitor will receive current, it will energize. When the voltage reverses, this capacitor will charge the inductor. When this capacitor discharges to the inductor will charge, but at the same time, this resistor will limit the amount of voltage that is stored in that inductor. While this inductor now discharges in the form of an electromagnetic force, or rather in a magnetic force, it will then charge this capacitor C2, and then after charging that capacitor C2, the capacitor C2 will carry all that voltage, throw it up to the bulb. We will have a glow, but there will be just that small glimpse of distortion or some waveforms playing. But everything is just working up together. However, the problem is that once in a while, we are going to have that small waveforms and then some spikes, and then some spikes. What will create those spikes? The inductor will be the one creating those spikes. However, the resistor is able to suppress those, though we need to use now a variable resistor, which of course needs to be controlled manually. But what happens to a scenario where we completely remove now this inductor and leave only the resistor? This means that when current is flowing in this direction, both capacitor C1 and C2 will charge and the light will glow. When the voltage decides to move in this direction, capacitor C1 will energize C2, or rather will continue supplying voltage, the same amount of voltage used as received to this diode. When this one discharges, C2 will take over, supplying the same voltage, such that when this one returns, the voltage which has been supplied is still received by this, and yet the two capacitors charges. At the end, we have achieved our DC output. Like I had said, it may not be a complete straight line because of some few distortion and some harmonics appearing there, but we would have achieved our DC output voltage. Now, this begins from a half wave rectifier, a full wave rectifier, both center tap and full and bridge rectification, going back to a simple capacitor filter. After a simple capacitor filter, we have an LC, or rather an RL filter, or an inductor filter. Let's call it an inductor filter. This is an inductor filter. After an inductor filter, we had introduced a capacitor here that makes it to be an LC filter. After an LC filter, we'd introduced a second capacitor there. This makes it an LC pi filter. An LC pi filter, the pi represents two capacitors. After an LC pi filter, we then did an RC pi filter, as you can see here. Go study those filters. Look at the examples that are there in your TVET First textbooks. Follow those examples and the steps provided to you. Also, look at the circuits which are there, but most importantly, find the differences in all the equations. They may look very similar, but if you study them as they are made so simple in this book, you will then realize that there is nothing so complicated about this module. That's it for me today, folks. Let us meet next time when we try to unpack some examples of this filtering circuit and then move on to the next.